It's my pleasure to introduce Dr. Pawan Gupta. Dr. Pawan Gupta is currently a senior scientist of Earth Sciences at the Science and Technology Institute of University Space Research Association USRA at NASA, NASA Marshall Space Flight Center, and his main expertise is in the application of remote sensing or satellite remote sensing for air quality monitoring and assessment around the world. So I'm really happy to have him over here, especially since the fact that so the year was 2004. A movie called Swades was released, and I was in class 10th. So it was a big, you know, it was a big moment for me. I really realized that, what is satellite, what is remote sensing, how all of this is engineering. I could not go to NASA, but I'm really happy that someone from NASA is here with us to speak today. A very warm welcome.
Hello. Okay, can you hear me? Okay, great. So, since you talked about the Swadesh, I just want to let you know that you might remember that Shah Rukh Khan was project scientist for a mission called GPM, Global Precipitation Mission, and that was finally launched in last 3 years ago. So, if you meet Shah Rukh Khan, you can tell him that that mission has been launched and it's giving the data. So I'm fortunate enough actually where that in the building where the movie was shot. In one of the, I used to work there for a few years. So thanks Nipun. So I'm going to talk about how various aspects of what we do at NASA, mainly focusing on air quality measurement from the satellite, and then bringing some of the citizen science aspect to validate the satellite data, how we are using them, and what's our upcoming plan. And in the last, I'm going to talk about some of the NASA is putting a lot of efforts in training people to use the satellite data for real life applications, such as air quality monitoring or crop monitoring or water quality monitoring or drought monitorings, land use change monitoring, all the things which we use in day-to-day life, how the satellite data can be used. So we are trying to build the skills in professionals, not only the students or the academia, but to the agencies who are operationally working on those specific application on day-to-day as their job. So we are trying to put a lot of efforts there as well. So I will give you some glimpse of those programs as well. Okay. Okay, so I think everyone here is familiar with impact of air pollution on your health, right? So I'm not going to talk a lot about that. This is the only slide I'm going to show. Basically, if you go on World Health Organization website, this is what numbers you will see flashing on their website. And these are based on the estimates, based on the information which we have available. And this is a global efforts. Community of scientists came together and tried to do all these studies, and they came with these numbers, and these numbers are really very dangerous in terms of 8 million people die every year just because of the air pollution. Either it's indoor air pollution or outdoor air pollution, and they are linked directly or indirectly with the air pollution. And if you see in terms of the numbers, 93% actually, sorry, I'm messing up. Okay. So the 91% people actually live in areas which air quality, according to WHO guidelines, is not safe for breathe. Okay, so that's a huge problem. Now, what we can do about it? So when you see all these sources, right, on the ground, you can see there is a, when I was coming to the IIT, I saw there is a power plant and it was basically emitting a lot of smoke in the atmosphere. So you can see those sources, some of those sources visible. You can also see smokes and other pollution coming out from industry or the vehicles or the burning. And often you can feel it. Means I don't know how things are here, but if you go to Delhi, you can smell it. You can feel that there's some people who has asthma problem or small kids or elderly people, they can really feel it. But feeling and seeing is not enough, right? You cannot just control using those things. So from the satellite, what we do is we can also see the same thing from the satellite. And this is just one example from a satellite called Deep Space Climate Observatory. It is located in a orbit called L1 orbit, which is about 1 millionth mile away from the Earth, which is about 101.5 million kilometer away from the Earth. So it does, since it's so far away, it can see both moon and Earth together. So this is on the left, you see moon and Earth together. This satellite provides image every 90 minutes of the daylight portion of the Earth. And when you zoom over certain areas, depending on the specific air pollution event, so in this case I'm showing an example from a fires in California, US, which was happened last year in October, and you can see those thick plume in that zoomed in area coming out from those fires. So sometimes these pollution events are so big you can actually see from really far away in the space. And that is the capability we are trying to use, that we just don't want to look at them, but we want to extract the information about them. We want to quantify them. We want to use them in making policies and decisions. We want to use them to mitigate things. We want to help communities to overcome these problems. So this is why we are trying to use the satellite data. And just by the way, whatever I'm showing here, all the data are in public domain, anybody can use. Most often you will see a website address here on the bottom. So if you are interested, if you are online right now, you can just go to this website and you will be able to see these images in real time as they come. And anybody can access that images. Okay, now what you have to do in order to make the policies or decision, or you need to make measurements. You need to know how much quantity of air pollution is there which we are breathing, right? And it's not only one pollution. There are a number of different type of pollution. There are particles in the air, and there are gases which are harmful to our health, right? So there's NO2, SO2, ammonia, formaldehyde, and many other gases which are there in the atmosphere. So in this particular map, what I'm showing is the locations on the Earth where we have set up ground monitors. And this is, when I say we set up, it doesn't mean that NASA or I have done. This is done by individual government from individual countries, which regulatory agencies, like in India we have Center Pollution Control Board or State Pollution Control Board. Every country has their own environmental agency, and they put this regulatory grade monitor which cost really I think in Indian rupees it's more than 1 crore rupees to set up one of these stations, and then the maintenance is separate. So you have all these data sets available, but you can see on the map there is a huge gap over African continent or South America, even over India. In India we have about 130 regular continuous monitoring station which gives measurement every 1 hour. There are other stations which make measurement on a other time interval. In China they have a 1400, and there were studies which project that India need at least 4,000 of these stations to really map their pollution at the scale which can support the population density. So there is a huge gap there. So what we are trying to do is, how can satellite help to fill some of this data gap from the space? Okay, so what you get from the satellite, let me see if I can run some of the movies here. So what you see from the satellite, when satellite overpass certain area of the Earth, it takes pictures. Think satellite as a really advanced camera which you have on your phone. Okay, it's a really very sophisticated version of the camera. Very accurate, very high spatial resolution. So what satellite gives you, it gives you this kind of images. We call them true color images. We make them by combining 3 different channels, red, green and blue, and they are true color because you see the colors of features as you can see from your eyes. So if you look up in the sky, clouds will look white, the smoke will look little bit grays, the dust will look brownish. So similar colors you will see in these satellite images. So you can really identify while looking different features. So what these images are showing is that satellite not only can see these big pollution event, but they can also, if you look them really carefully, if you train yourself a little bit more, you can identify different features in these images. You can identify clouds, you can identify smoke. So these are smoke actually over from Indonesia. It's on the right top. There was a huge fire in 2015 in Indonesia, and it put a lot of smokes in that. You can see smoke and clouds. Over Australia, you can see actually this is every 15-minute loop on the top left corner, where you can see smoke coming out from these fires and how that is converting into cumulus cloud actually. And then you have over India, fog and smoke, which is again every 10-minute satellite data. In northern India, you saw the fog conditions happens every December, January. It's a huge problem because, so you can monitor that very carefully as sun comes and the fog actually start disappearing. And then the volcanic eruption, dust and many other type of pollution you can see. So you can see very clearly from the satellite data when these events happens on the earth. But again, our goal is not just to looking, I mean these pictures look amazing, right? Pretty picture, but that's not the goal. What we are trying to do is, can we convert these images into quantified numbers? Okay, so there's an old saying, right, which says a picture is worth 1,000 words. When you see picture, you can talk a lot about that basically. So I try to convert that into a little bit different, that a satellite picture is worth millions of data points. Okay, so if you have to make measurement on this area, this is again showing some fire images from the in the Russia, in Siberia area. And if you have to make measurement, then you have to put hundreds and thousands of stations to make measurement on every single grid points. But satellite is giving you actually a quantitative value on each of those grid points. So each pixel, some of you are a computer science student, right? You understand the pixel which you see on your TV screen or on your computer screen. So each pixel of the satellite imagery has a specific geophysical value which can be quantified and which can be used for scientific purposes. Okay, so now the challenge is what is that value is. Okay, what geophysical value that is. So anybody knows what satellite make measurements of? Anyone familiar here with the satellite, how satellite operates? Okay, so most satellite, there are two types of satellite. One is called passive satellites and one is called active satellites. So the active satellite is basically this thing right here, which has a source. Okay, so this pointer has a LED which is basically putting out the laser beam. So this is considered an active satellite. It shoots the light and then it reflects back. There is a telescope which receives the light. But in this case, most of the satellites are passive satellite, means they rely on the energy coming from the sun or emitting from the earth surface. Okay, so when then there is a sun out, it emits solar energy in a different spectral channels, in visible part or IR part or UV part, and then it interact with the component in the earth and atmosphere, right? So on the earth surface you have a different pieces, like you have trees, water, glass, land, buildings, roads, all the things which we are there on the land. It interacts with it, and it also interacts with the component in the atmosphere. In the atmosphere, what we have? Clouds, particles, lot of gases, right? Oxygen, nitrogen, ammonia, NO2, all the gases are there. So it interacts with all those things. And when it interacts, depending on the wavelength of incoming solar light and depending on the property at which of the object with they are interacting, its intensity changes. Either it will scattered or it will absorb or it will transmit it depends on that, right? So once that goes back to the space, the part of the radiation which is reflected back to the space is measured by the satellite into different spectral channels. Okay, so that is what satellite is making measurement. It's making measurement of the reflected light in different spectral channels. So it does not making measurement of air pollution or particles or gases or clouds or anything. It's just that radiance value. Okay, so just remember that when somebody says satellite make measurement of this thing, it's basically making a radiance measurement which we convert into different pieces of information. So what we do to convert that into a quantity which we can understand, like temperature. If I say radiance is 4 watt per meter square per microgram per steradian, it will not probably make sense to a lot of people, right? But if I say temperature outside is 25 degrees centigrade, you can kind of feel it, right? What will be, whether you need a sweater or you don't need a sweater type. So we want to convert that into some quantity which we can understand and which we can use, and that is where the geophysical quantity comes into the pictures. So what you do is we have this measured spectral radiance. Let me try my I think I have this pointer is not pointing. This.
So it's one thing, but it is not on one side, so you need to use two.
It does. Oh, okay, that's fine. Thank you. Yeah. So what you get from the satellite is this spectral radiance, and then you make some assumptions about what you are looking. Okay, so that's called a priori information, and then you do use some physics equation. How many people have heard about Maxwell equation, right? You studied, everybody, in the physics, right? So Maxwell equations, that's where the satellite remote sensing starts. You start from there, and there is something called radiative transfer theory. So you calculate how much radiation should be going back to the space because of all this interaction. That's what the radiative transfer theory does. So the goal is here to simulate exactly what satellite is making measurement by making some assumption, and we call it generating lookup table. Once you have lookup table generation from this piece and this piece, then you compare these two pieces, and that is called the retrieval algorithm. So you have a simulated radiance and you have a measured radiance. Now in measured radiance you don't know anything that where this thing's coming from, right? Because there is mixture of signal, it's coming from cloud, aerosols, gases, surface, everything. But the simulated radiation, you know exactly how you got those. You know the quantity of aerosol, you know the clouds, you know the surface, you know everything. Now you mesh the two and minimize the error. Where the error is minimized, you say, okay, for this measured condition, this is what my quantity should be for particular. So that's how we retrieve, and it is called inversion algorithm. Means there are assumptions, so there is definitely uncertainties in those estimations. So that is the retrieval algorithm. Once you get this geophysical parameter, which is for air quality we called it aerosol optical depth, and I will explain it a little bit later, and then you use for application like air quality monitoring. Okay, now let's see how satellite in a given day make measurement, right? So this is example of a satellite called MODIS, Moderate Imaging Spectroradiometer, and this satellite is on board on the two satellites. One is called Terra and another one is called Aqua. Terra makes measurement in the morning time, and then the Aqua make measurement in the afternoon time. So there is about 3 hours time window between the two. And what this satellite does is it rotates around the pole. So it's pole to pole, and then the earth underneath rotates, right? So whichever part of the earth comes under the satellite overpass, it make measurement at that location. And that's how these orbits are created actually. So on a given day there are 14 different orbits which goes all around the in the white, and then we retrieve this quantity called aerosol optical depth, and that's what this is color coded here in the scale from 0 to 1 at 550 nanometer. And anybody can tell me what is those white space on the map? Why I don't have data everywhere? Any guess? These are clouds. Okay, so when there is a cloud, we cannot see through the cloud, so we won't we see the particles which are underneath the clouds. Okay, so we first identify the cloud in the image and throw that data and only use the cloud free data. Okay, and you also see there are gaps in the polar region, because polar region we usually have ice or snow on the surface and it is very reflective, so you cannot get enough signal from the particles, so we don't retrieve, because if you retrieve there will be huge uncertainties, so we don't retrieve those areas. So once you start accumulating this data, you can create these global maps of aerosol field or air quality field, which will be able to tell us a little bit more. So what I did is, in the next slide, is created this seasonal map. In this seasonal map is basically showing what is the spatial distribution all around the globe of these particles in the atmosphere. Just think about this aerosol optical depth is the loading of particles in the atmosphere, entire atmosphere. Okay, and in the winter, spring, summer and fall season, and if you look a little bit more carefully, then you can really identify different sources of these particles, major hotspots all around the world. You can see dust coming off of the Saharan deserts during the summer and spring seasons, biomass burning happening in Africa, pollution happening in actually over in IGP region during the spring because of the dust, and during the fall season because of the biomass burning in other regions. There's a lot of burning happens in South America in Amazon forest. So there's a lot of thing going on all around the world in terms of the major pollution events which put out either smoke or dust or pollution in general from the vehicles or industries. So you can actually look these images and identify, and this is only possible from the satellite. You cannot do this from the ground measurement, because in order to do the ground measurement you have to put really millions of stations on the ground, and that's kind of not cost effective in a way. Okay, I don't know what I did. Sorry about that. Now let's look what is this aerosol optical depth is. So the aerosol optical depth is basically an optical property. It tells us how much light will be attenuated by these particles as it passes through the atmosphere. So if there are aerosols particles in the atmospheres, then it will interact with this incoming solar radiation and the light will be attenuated. When I say attenuation, means it will be reduced or increased based on the properties of the aerosols, right? So the scattering process happens. People who studies in physics, right? You study the scattering and absorptions by particles. So that's what is happening in the atmosphere. And that attenuation is we can quantify in terms of aerosol optical depth. It represents entire column from the surface to the top of the atmosphere. When we talk about the air quality, we try to measure what is our nose level pollution is, what we are breathing. Okay, and that is done at the surface. So if you see that small box, that's where the air quality measurements are taken. Okay, so you have these instruments like pollution control will puts out on the ground or on the top of the building, which make measurement of this particle, either it's PM 2.5 or PM 10 or PM 1. And these two quantities are different. Okay, this is a physical mass you are making measurement, whereas this is an optical property. So just let me tell you how these are different. So if you differentiate between these two quantity, what you get from the satellite is called aerosol optical depth, is a column integrated value, means from surface to top of the atmosphere. It's an optical measurement, it's not physical mass. It's a unitless, there is no unit of aerosol optical depth, and it's a function of shape, size, number of particles in the atmosphere, and where are they in the atmospheres. All those things actually, and at which wavelength you are making measurement, which solar wavelength you are making measurement. All those properties will is function of actually aerosol optical depth. And then on the ground, what you make measurement of PM 2.5 is a dry mass. It is measured under controlled condition. When you make measurement, you heat the air actually, and to bring it at the 40% relative humidity. It's a dry mass of particles less than 2.5 micrometer in aerodynamic diameter. So it's a very specific definition. It's only certain range, size range of particles which you are making measurement. So there are number of difference between these two quantities, but one thing you remember is both are making measurement of number of the particle loading in the atmosphere. So there should be some relationship between these two quantities, although they are different in their physical or in their definition terms. Okay, so the next thing comes, how do you, once you get these quantities from the satellite data, how do you know whether they are right or wrong, right? So to do that, what we call it validation. So in order to do the validation, you need some ground truth. Ground truth means you have to make measurement at the ground using instrument which can provide, like I said earlier, satellite does not make direct measurement. You're taking that radiance and converting that into aerosol optical depth. So it's an inversion process, so there is assumptions made, so that creates uncertainties, right? So how do we know what kind of uncertainties are there? You have to quantify the errors in what you get from the satellite. To do that, we use this network of ground sun photometer which makes measurement of aerosol optical depth very accurately within 1 to 2% error bars, and they are considered as gold standard for aerosol optical depth measurement. There are about 600 stations all around the world operated by NASA, and the main purpose of this station network is to validate the satellite data. And there are a number of stations in India also. So when you do this ground truthing, let's see how the performance looks over India. So there are certain number of stations over India, and when you compare the two measurement, so the y-axis is what you get from the MODIS aerosol optical depth, the satellite aerosol optical depth, and the x-axis is what you get from this aeronet measurement, the sun photometer, which is making measurement at the ground. And when you compare the two, you will see a very good tight correlation. Of course, you will see a scatter between the two quantities, means there is uncertainty. And there's number of reasons you have to understand. One is, although both of them are making aerosol optical depth measurement, but they are different. In a sense, the sun photometer is making a point measurement. It's looking at the sun and making measurement at that location only. So it's represent only that area whichever the sun photometer is looking. Whereas the satellite has a footprint, it's a size, in this case it's a 10 kilometer, which is 100 square kilometer. So it represent average value for large areas, and things can change in that area. Second, satellite, you are getting only one measurement from the satellite at instantaneous. So satellite is passing over Gandhinagar IIT at 10:30 a.m. So that's the time when the satellite is making measurement. Whereas the surface is making measurement every 15 minutes. So there are differences in terms of measurement, but the overall correlation suggests, and if you look the bias number, probably it's difficult to see, the mean bias is about 0. So on a global scale, on a larger area scale, they are very good, considered very good results from the satellite, and the uncertainties in these numbers varies. On average, it's about 15 to 20% on a global scale. Okay, now this is about the aerosol optical depth, but we also convert this aerosol optical depth into PM2.5, and to validate the PM2.5, you need this regulatory measurement from the pollution control board type of agencies all around the world, the same map which I showed earlier on the left. And then, like I said, these are not enough measurements. So now we are trying to explore this new type of sensor which are very cheap. Like earlier I said, the standard quality measurement cost about 1 crore to set up one station, but these are very cheap. They can be $100 to $1,000 kind of range, and these sensors, since they are cheap, you can install them in large number. But the biggest concern of that is, are they reliable? Are we getting the same quality of the data which we are getting from the standard? So that's a big question, and in one of our project, we are trying to evaluate that. We're trying to see how good those sensors are, how much we can use along with the satellite data to get the better air quality information. Okay, so another application I just want to show quickly, even if you do not convert that aerosol optical depth, that column value which you get from the satellite to PM2.5, still you can use aerosol optical depth for a lot of application which will inform you about certain things. So in this example, just showing the value of aerosol optical depth. So this is a time series annual mean number over northeast United States on all those stations. And I chose the US because we have a long-term measurements from the surface on those locations. And what you see on the top is a time series annual mean with the standard deviation from the surface measured US EPA measured PM 2.5 from 2003 to 2014. And if you look this, if you try to plot a trend line, then you will see about 30%, 35% reduction in PM 2.5 in that part of the world over last 12, 14 years. Okay, so that is coming from the regulatory grade, very accurate measurement which is made by US EPA. Now, if you look the same thing in terms of aerosol optical depth from the satellite, which is I plotted on the bottom, you will see the standard deviation is large, means it's showing that there's a much more variability in the satellite data or much more chance of uncertainties. But if you look the trend line, then it does give you about the same number, 30% reduction. So this kind of shows that although these two quantities are different, although satellite is not making direct measurement, you are retrieving, but there is a value, it's showing, it's giving you same piece of information which you get from the surface measurement. So if you have to make a decision or a policy intervention or the mitigation strategies in places where you do not have PM 2.5 measurement, you can still use the satellite data and probably you will reach to the same conclusion. And this is just one cherry pick, okay? This does not mean that you will see same kind of correlation between these two quantity everywhere. This depends on many different parameters. Okay, another example from India. So this is, now I don't have that long-term time series of surface measurement over India, so I'm going to just show what satellite is showing over India. So what you see on the top map, actually on the left side, is a long-term mean aerosol optical depth from 2003 to 2007 map of aerosol optical depth, which ranges from 0 to 0.8. The darker color, the red and magenta color, shows the high values. And you can see in the endogenic plane there are very high values, right? And this is during the post-monsoon season, means this is averaged for October, November, December, I believe. So this is post-monsoon. And if you look the later period, which start from 2008 to 2014, you can see huge increase in aerosol optical depth in that region. Okay. Now on the bottom, what I did is actually I took that box and average and then put a time series for that entire period. So if you look from 2003 to 2014, during the blue line showing the post-monsoon, it clearly shows an increasing trend. If you do the same trend line, same time series during the pre-monsoon season, then you don't see that clear signal of increasing aerosol in that region. So there's another factor coming here is that this increase in aerosol loading in IGP is not year around, it's a specific season. It's a seasonal, and that basically indicate about some of the activities or practices which we do in a specific season, or some of the conditions which are happening in that region. And now, so this is more kind of a regional analysis. Now you can actually go back and do the same analysis for specific cities. So you may see Ahmedabad here actually in the third on the first column, right? Third row, first column, that's Ahmedabad. So it's about 25% actually increase in aerosol optical depth. And if you compare the values of mean values of Ahmedabad to Calcutta or Chennai, you will see actually they're much lower. So Calcutta, the mean value is about 0.7 aerosol optical depth, which if I would have to convert that, it will be about 80 microgram per cubic meter, just rough estimate. And then Ahmedabad is about 0.3 or 0.4 aerosol optical depth. But you can see that there is a continuous increase, means the trend is clear. It's not random. It's a very clear trend. And you can see in all of those cities, actually, Bangalore is really amazing. You can see almost 90% increase in last 10 years in aerosol optical depth. Still, it's a very clean but there is a huge increase happening in city of Bangalore. So you can use this satellite data at individual city level to see, now we have 20 years of records from this sensor actually to see what has happened in last 20 years. Are our policies working? Means, for example, you can see, I haven't shown for Delhi, but you can see for the Delhi also. Delhi started CNG gas in early 2000. Does that has any impact, right? Or there are more fire burning happening, is that going to change? So all those things can be seen in this data if you dissect them in a proper way and analyze. So there are uncertainties. These are not the same quantity as we get from the pollution control board, but still there is a value in it, in using it by standalone. Okay, now let me just talk a little bit about a case study using the citizen science, the low cost sensor which we did actually in California, trying to quantify the impact of fires using both satellite data and these low cost sensors. So what we did is we used the sensors called, there's a company called Purple Air which makes this sensor, and there's many other companies which make similar sensor. And these sensors are very small. You can see it actually here on this. They can be mounted on any platform, on a building or anywhere. They are like this big. And only thing they need is a power connection and a Wi-Fi connection. The Wi-Fi connection is to transmit the data in real time. And once it is connected to Wi-Fi, there is an online map, and you will start seeing the data immediately. It collects data every minute and produce and you can see on the map immediately. So we selected that, and what we are trying to do is we are trying to buy a large number of these sensors, and we will concentrate on a small area. So we did a study in California where we put like 50 sensors all around the Los Angeles city area, and so that we can actually map the spatial gradient which we see from the satellite, like in this image. This is from the satellite, and we put monitor in each of these satellite grids so that we can have measurement, simultaneous measurement from the satellite and from the surface together. And we plan to do the similar experiment actually next year in India in IGVP to see this spatial gradient. So let me just show you some results from the California. So one of the thing I was telling earlier is one of the concern when we use this low cost sensor is the quality of the data. Are the data reliable from these sensors or not? So if you look, we did this study where what we did is we put this lot of these sensors, in this case 6 sensors, close to a standard monitor which EPA produced, right? The one which is very expensive. We put them together in the same place under same environmental condition, and all of them are making simultaneous measurement, and we start comparing them, and we run this experiment for 3 months in the field. Okay, so what you see here, I don't know if you can see the lines very well, but this line, the black line, is from the standard measurement, and all other lines are from the low cost sensors, and the dotted lines are for every hour values, and then the solid line is for a daily mean. And one thing, multiple thing you can notice. One good thing, positive thing you can note is both standard and the low cost sensors are following diurnal cycle, hourly how things are changing, and also from day to day how things are changing. So both of them are following diurnal cycle and day to day cycle, which is a positive thing. Good thing means both are responding to change in air quality in that particular location. Now if you look a little bit more closely, then you will see that most of the time the low cost sensor are overestimating, specifically in the condition where the PM2.5 values are larger. So you will see all these lines are very huge compared to this black line. Only in some cases when there is like very clean condition, your low cost sensor is underestimating, otherwise it is often overestimating. And we did this in you can see that actually in the bottom plot here. This is the PM2.5 measured using the standard monitors, and this is the difference between the low cost minus the standard measurement. So up to 10 microgram per cubic meter under very clean condition, you will not see much difference between the two measurements. Mean the low cost sensor is performing really well compared to the standard, and we can believe the data. But as the PM2.5 started increasing, again this is conditions in California, this will be very different in India. Okay. So what you see is the bias between from the low cost sensor started increasing. That is okay, means we can deal with the bias. If we know the bias is systematic, we can correct it, okay. But the problem here is, if you look this spread, these are different line for different units of low cost sensor. Although they are made by the same company, they are supposed to be identical, they are supposed to be making the same measurement, but still there are difference in their measurements. So this is really big concern, because if you do not have consistency among the same unit, then you will not never know whether measurements are real or artifact of the instruments. Okay. So we are trying to see how we can overcome with this specific problem. So looking at that problem, let me show you some result. So the first step was to understand the sensor itself. And the next step is we did actually deploy a lot of these sensors during a fires in Bay Area near the San Francisco airport, which happens last October. This is like a smoke coming out from these fires, and we published this study very recently. And let me show you some result from that. So if you look this is another sensors called VIRS. This is on board and another satellite called NPP satellite. Again, it's a partnership between NASA and NOAA. And this specific sensor is a little bit higher in a spatial resolution compared to MODIS in a specific channel. So on October 8, 2017, you see this specific area in California, Bay Area, you won't see anything. Things are very clean, conditions are clean. If you see October 9, the fire started sometime late night of October 8 actually. October 9, you can see lot of fires started, and the smoke coming out of these fires you can see from the satellite image. So you can visibly see that fires are happening and the smoke's coming out from these fires. Now there is another algorithm from the satellite which can actually detect individual fire, which will tell you exactly the latitude and longitude of the fire where it is happening. So it's a very high resolution data, 375 meter resolution. So if there is a fire in that big 375 by 375 meter area, the satellite will detect, and it will give you a latitude, longitude, and there are other parameters which will tell you the intensity of the fire. And again, it may not be visible from the back, but this October 8 you won't see anything. On October 8 there are some red dots start showing up in this map. These red dots are the locations of the fire which were burning at that particular time on that region. There is another kind of measurement during the night. So these are only daytime measurement. But what you do with the nighttime you don't have a sun, right? So you cannot see images like this during nighttime, because to get this type of image you need sunlight. So in the nighttime we use another band, it's called DayNight Band. So the DayNight Band is basically taking pictures of city lights, anything which is lighting up in the nighttime. And they are very sensitive, even there is a small source of light it can detect actually. And you can see again, if you look the same circle, there are hardly any lights in this region. October 9 when the fire started, the light coming from the fires are visible in this DayNight Band of the VIRS satellite. And if you look a little bit more carefully, the smoke plumes are also visible, because the lights are scattered from those smoke particles in the atmosphere, and that get back to the space and satellite is capturing. So again, there is another piece of information which we are getting from the satellite to confirm what is happening in that region. And these are very useful information for the fire management agencies, people who are firefighters who are trying to put out these fires actually. And then finally you want to quantify how much smoke is coming out from those fires. So for that we retrieved aerosol optical depth. Again, on October 8 you don't see much values, the things are very under clean condition. October 9 values are very high, larger than 1. Now the question is, can we convert that into PM2.5 or air quality information? Okay. So what we did is we used this low cost sensors in that region, and this is the area where we actually have a huge density of these sensors, and we measured PM2.5. And what you see here, this number is basically change in day. So these are the numbers of October 8, 9, 10, 12, 13, 14, 15. So these are the days of October. And what you see on the left side is the measurement on those specific location where we are making ground measurements from the satellite. So this is aerosol optical depth. Blue means very low values, red means very high values. And on the right side is the surface measurement of PM 2.5 from those low cost sensors. And if you look carefully, then you will see that on October 8, 7, 8, the values are very low. October 9, when the fire started, both started showing up, right? So both surface measurement and satellite measurements are responding to change in number of particles in the air due to those fires. How much they are changing, that's a different question, we will come to that. But both are responding in the same manners. Means if smoke particles are going up in the atmosphere, both are showing up higher values. If they are going down, they both are showing the down value. So that's another indicator that yes, both low cost and satellite are useful, providing some useful information. Now the next question is, can we convert that into quantitative values? Can we map the region using the satellite data alone in places where we do not have this measurement? Okay. So to do that, what we did is we used some machine learning algorithm. We combined what we make from measurement from the surface, satellite data, meteorological data, because wind speed, temperature, relative humidity, all that actually impacts how your PM 2.5 will change in that region. Depending on the wind direction, things can change, right? So we use all this information, did a machine learning algorithm and created maps. So this is the region we use, and then we created maps based on that trained algorithms. And this is a weekly average, 1 week average before fire, 1 to 7 October, 8 October I think. So this is before fires, and this is during the fire from October 8 to 15, and you can see very high values of PM 2.5. So on a weekly scale, 50 microgram per cubic meter is very large value in that region actually. So again, if you do a little bit more, go from aerosol optical depth, combine with other data sets, use machine learning technique or any other statistical modeling, you can come up with these maps and identify areas where the pollutions are have large values. Okay, so that was experiment. How much? 5 more minutes? Now I'm going to go very quickly showing some of the upcoming missions, satellite missions on the air quality. So whatever we were showing, they were like 20 years old instruments. Okay, so one thing is, like I was talking about the polar orbiting satellite, which gives you one measurement in a day, and that's how that sensor is making measurement. So it's passing during that night time, in daytime it's making measurements, and that's how the Earth is feeling in a given day. But this is not enough. You are getting only one measurement, right? So we know that the air quality changes from morning to evening to the afternoon and in the night, right? So we need a continuous measurement. We need more frequent measurement. So to do that, we are using a new generation of satellite called geostationary satellite. Okay, these were not available earlier. They became available in last 2 years only, and they are providing now as good quality of the data as we were getting from this LEO orbit, the low Earth orbit satellites. And the advantage of this satellite is they are sitting at 36,000 kilometers above the Earth and looking the Earth all the time. So they are stationary with respect to the Earth. So you can see a specific region of Earth all the time. They can give data every 30 seconds. So the disadvantage of this satellite, it's only going to cover one part of the Earth at a time. So if you have multiple satellites, so there are currently there are 3 sensors. One is from US, one which covers entire America. There is a European sensor which not as good quality as this one, but they are planning to launch in next 2-3 years. And then there is a Japanese satellite called Himawari. So if you combine these 3, you get a global pictures every 10 minutes. Every 10 minutes, one observation for entire globe. That will be game changing in terms of how we monitor things compared to what we have. This is just showing an example of how we can use that high temporal resolution information and showing some biomass burning event actually in Canada and in South America, This is from the GOES-R satellite. You can see smoke plumes coming out from these fires in both Americas, and you can take these measurements and use some of the algorithm which I was showing earlier and convert into the air quality information, and you can see very unhealthy conditions of air quality under the fire conditions in that. So we can do all these things using this new generation of satellite. There are plans to launch more of these satellites. There is a constellation of satellite which will be up in next 5 years. It's called Geo Satellite for Air Quality. It's one of them is launched by US. It's called TEMPO, Sentinel-4 by ESA, European Space Agency, and the GEMS satellite which will be launched by Koreans, which will cover. So this will provide a global view of how air quality is changing. And the most important, the next step, once you have all this ground measurement, satellite measurement, what you do with that, right? You can only mitigate if you know in advance that what is going to happen tomorrow or what is going to happen tonight or in evening. Then only you can plan your activities. If you are planning to go on a run in the evening, and if you don't know what will be the air quality, you might harm yourself rather than getting healthy actually, okay? Because if air quality is bad, then you are basically getting harm. So to do that, you need forecasting, and measurement alone cannot do forecasting. You need model to do the forecast. So model can only tell. So once we put all this information which we get from the satellite at the ground, and then combine with the physics and chemistry understanding and put together a geophysical model, it will tell us what will happen in next hour, next day, or 5 days from now. And that's what we have done here. So this is a NASA model which takes all of the satellite data and then forecast up to 10 days in advance. There are still validation issues, and we are still working on them. But if you look this is same fire which we are looking in the satellite image. You can see individual fire, how the smokes is coming out from those fires and transporting with the weather system in large distance. The blue color shows actually the aerosols coming out from the ocean surface, right? Sea salt, and then this is basically dust coming out of the Sahara, and all these aerosols are mixing with the weather system and transporting to the long distance, and you can only do this using the model. So the model is the key in making sure you close the loop. So you have ground measurement, you have satellite measurement, and the model, and when you have all this integrated system, you can not only quantify what happened in the past, but you can also forecast for the future condition, and then you can take steps forward about what to do on those conditions. So with that, let me very quickly go over about the capacity building program. We have like 3 different programs. One is the training program where we do the online training. This is the develop where we work with the students and the end user agencies who wants to use the data and develop a specific application, and then the use. And then the SERVIR is basically another program where we go to the developing countries and help them use the satellite data to mitigate some of their real life applications. So I'm not going to, since we are running out of time, I'm not going to go into details, but there's a lot of information available online on this. And this, I just want to show you, if you really if you are curious to see satellite data yourself, this is the tool where you can get. So if you just type on Google World View NASA, then you will come up with this tool, and what this tool does is it provides satellite data in real time. So if satellite is overpassing over IIT Gandhinagar, within 2 hours you will get image for IIT on this tool. You can look it up here, and you can see many, I think there are almost 600 different parameters which you can visualize here. You can superimpose, you can do animation, you can make PowerPoint, social media post, and you can also access on your mobile phone. So with that, I think this is just an example from that WorldView tool I just created. This is last 1 week fires overall India. You can see all those red dots on the left, and on the right is basically RGB images showing some of the pollution movement in last 10 days over India. Again, these are just created using the tool which I just showed earlier, and it's available. All the data from NASA satellites are available for free for anyone to use, to download. There's no restriction, you can use for any purpose. Even if you want to make your own product and sell it, feel free to do it. Um, so they encourage actually, and we trained also for people to do that. So with that, I think I'll take any question. Thank you.